Okay, so this week you're going to start to get some answers. They're answers that will not be right in any way, shape, or form, but they're answers that are pretty close to right. So what does that mean? Remember I said at the beginning, the architect often does kind of a preliminary concept and layout, and usually draws a few quick sections and probably gives some depth to things. Well, that is what you are going to be able to do at the end of this lecture. Now, I'm going to be honest. What you learn at the end of today's lecture is probably the most architects will do going forward for the rest of your career. After today's lecture is probably what you will do when you're out practicing in the world. We're going to spend the next term and a half teaching you all the math that is the right answer to things. But that is to help you understand why what I give you today is pretty darn close to right. What I'm giving you today is not right, but it is what most architects do to get answers that are almost right, because you guys aren't the engineers. So like I said, the next term and a half is all about showing you what the engineers actually do. Because it's important that even if you can't do it by the time you're done graduating, that you understand what your team is. It blows my mind what architects have to understand. You have to have a good grasp of everybody else's scope. Your scope, you have your own scope, plus you have to understand parts of everyone else's. And I find that truly amazing and impressive. So that's what we're going to be doing going forward. Today, though, you are going to learn what we call the sizing guidelines. And so this is what you would be able to put on a set of preliminary or even probably schematic design drawings. So we're going to talk about what the sizing guidelines are, and then we're going to look at the sizing guidelines for the major structural material types that we talk about. And then we'll go through some examples. The math is not hard. It's very, very, very simple math. What I find throws people off is some people just have a hard time kind of getting their head around what's going on. It's once it clicks, and it's a surprisingly not difficult concept. So if you're struggling, take a breath and kind of just look at a drawing, or stop and think about what we're trying to figure out here. Okay, so I am going to tell you that for the first time in a very, 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 very long time, there are no kids in my home. I'm very excited about this. The bus is running, daycare has staff, and Malcolm's class does not have COVID in it. All the other classes have COVID in it, which means it's inevitable that his class will have COVID in it. But for now, we're just going to relish in being able to get a solid day's work done, which it has been a very long time. All of the time I've had to work has gone into teaching, and I have a list of very angry emails that I've been pushing off. Okay, so again, there's not a lot of math today. It's a relatively short lecture. At the end of this lecture, if you find you're struggling or you want to practice a little bit more, go back to any of the drawing sets that I've given you. Whether it's that set of a typical building that's not typical at all, but it really kind of shows all the things we talk about, or one of my projects that I've worked on, like the Gold Ring Center or the Cube Lofts. And try these sizing guidelines on a few members and look and see how it compares to what's on the drawing set. Because what's on the drawing set are final designs. And you will see that most of the time, they're pretty close to each other. And there are a few that are nothing like each other at all. And that's where the final design is very, very, very important. This is just going to be a pretty good guesstimate. So, sizing guidelines, what are they? Some people will hear the term rules of thumb. Almost every industry has their rules of thumb. One student one year in the reviews accused me of being sexist because there was an urban legend that went around in the 70s about what the term rule of thumb means. It is false. That is not true. That is not what it meant at any time, and it was a crazy thing that got started. In my industry, I've always referred to these as rules of thumb. Electrical engineers, plumbers, regular electricians, everybody has their rules of thumb, and it's pretty standard terminology. That said, I didn't want to offend anyone, so I've changed the name to sizing guidelines. The only reason I'm pointing out that you might hear it called rule of thumb is that often people will use ROT as kind of the what we're trying to do here. And if you're talking to someone else, they will probably refer to it as the rules of thumb. Okay, they're a broadly accurate guide or principle based on experience or practice rather than theory. So, this has been done a lot. Everything we do is new, but it's not that new. The process is similar. And because we've done this so often, we know what is normal. So as long as everything is normal, your beam will probably be this deep or this big. And that's really what we're doing here. We're kind of creating a list that you can adapt, or a graph, really, that we've just written down as an equation, that you can use in the world of normal things. So they're a guesstimate. They're not the right answer, but they're pretty darn close to the right answer most of the time. So they will give you an approximate depth of beam or column dimension. And remember, everything you need to know about structures, you already know. These rules are based on that. But if you look at it and something seems off, it's probably off. You know in your gut that something seems wrong sometimes. And we're going to talk about a few examples of that, where these sizing guidelines give us some information. And when you stop and think about it, you're like, no, that doesn't make sense to me. How can that be right? And that's when it's important that you understand that these are not always the answer. They're a starting point. Oops. Okay. How to use structural guidelines. It's a linear relationship between length and depth. So the length is how long the beam is, or whatever the element is, and depth is how deep it is. If we were talking about a column, instead of length, we'd be talking about height, and we'd be talking about width instead of depth as the dimension. So the depth equals the length divided by your rule of thumb, or your sizing guideline. Or D equals L divided by your guideline. That means you can rearrange it. If you wanted, you could find the length by saying the depth times the sizing guideline. So if you know how long the member is, remember, you're the architect. You're creating the layout. You are the one determining how long it is. That is your design choice. How long is this member? So you know that. If you know how long it is, you can figure out approximately how deep that member needs to be. Why is that important? And you heard me say this in the first lecture, I believe. If you have a maximum cap on the height of your building, and you know that you are trying to fit so many stories in there, and you draw each ceiling as this deep, and it turns out your ceiling needed to be that deep, well, that difference added up, say 10 times, might mean you have to remove a whole story from your building. Or maybe you just have an upper limit on a one-story building, and you've drawn it this deep, and it turns out it needs to be that deep. Well, everyone's going to go around bonking their heads on things. So knowing roughly how deep your members are is very important. Now, what if you're working on a project and you know you have a hard and fast rule that your member can't be deeper than this? There is a headroom issue. That is what bounds you. That is your limit. Well, then you can say, if I can only be this deep, I should be able to figure out the maximum length of beams I can use. And then you could set out your grid spacing based on that. But usually you are starting with a constraint of some sort in there. Sometimes it's a constraint you've decided on, like what is my grid spacing? When can you use your structural guidelines? They'll be close to the final designed member when they are within the range of normal application. So when might not it be in the normal range of things? Well, if you have really large loads, if it's doing something, if it's supporting something outside of the normal, people moving around, and normal in its application. So if you were designing the floor for gold bullion storage, that is outside of the realm of normal. Those are going to have really, really high loads on it. If they're spanning really long distances, remember in that sizing guideline chart I said it's a linear relationship? Well, I'm going to spend most of next year telling you that it is by no means a linear relationship. The final design proves that it is not a linear relationship. But in the realm of normal, it's so close to linear that we can assume it's a linear relationship. So if it's a really long span, that's when our guideline starts to fail us. If you're using a weird or unique layout, so maybe you have weird distributions of loads, that's going to change what would be normal in the building. If you have large transfers, or if you're using the material in a unique way. These are all things that could impact what your sizing guideline gives you as the answer. You'll get your answer from your sizing guidelines, but you need to know that if any of these things are happening, maybe your sizing guideline isn't the perfect answer. All right, what are the sizing guidelines? So if you guys remember, our corrugated metal deck, and so this is just a folded piece of paper here. Metal deck is very similar to that. We have the direction that it's spanning. Remember, it's not spanning in this direction because it's not doing anything. It spans in this direction. The distance between my hands is the length it is spanning, or L, that length that we're seeing right there. Depth is how deep these folds are. That is the depth. So corrugated metal deck, D equals L divided by 50. All right, here's where it's important to know that some things are only available in certain depths. Metal deck is typically available in 38 millimeters, which is 1.5 inches, or 76 millimeters, which is 3 inches. 38 is by far the most common and by far the cheapest. I've heard it said that the cost of the deck basically drives your system. Your deck, trying to lower the cost of your deck, can make the lowest building possible. So use your deck as kind of your starting point, and unless you have a reason not to, I would start with 38 millimeter deck. All right? And so when could you use 38 millimeter deck? Well, let's take a look. We know that the sizing guideline is D equals L divided by 50. All right, if the open web steel joists, so the open web steel joists are how far apart my hands are, or purlins, so my hands would be the purlins or the open web steel joists, are at 2 meters on center, or 2,000 millimeters apart, what depth of deck should we use? Now, these are really quick math calculations, so I'm not going to keep turning my camera down. What I used to do in the old school world when I was standing in front of you, I have a pen that I can write directly on my laptop. In fact, I bought this very expensive laptop specifically for that purpose, because there wasn't a means to kind of show calculations in real time, and the chalkboards were basically non-existent and hard to see. So I also have it worked out here on the screen, so I'm going to talk it through. All right, so our sizing guideline is depth equals length divided by 50. It's told us that this is 2,000 millimeters deep. So 2,000 divided by 50, we get 40 millimeters. Well, 40 millimeters is, I would round that, I would say 38 millimeters and 40 millimeters are the same thing. Now, we're going to see going on, further on, that we wouldn't normally go down in size simply because we want to be somewhat conservative. But I'm going to tell you that 38 and 40 are essentially the same answer. So, if the supports are 2 meters on center, we know that we could use 38 millimeter metal deck. So length is 2,000, sizing guideline is 50, depth equals 2,000 divided by 50 or 40 millimeters, 38 millimeter deck. Here's a question. If deck comes in 38 millimeters and 76 millimeters deep, we're going to say 38 is pretty darn close to 40 millimeters. And we know we would use corrugated metal deck most of the time. This means that whatever supports deck shouldn't be any more than 2 meters apart. And 2 meters apart is a pretty good assumption. So if you see 38 millimeter metal deck, you know that its supports are probably around 2 meters on center or somewhere below that. That also means that if you have 38 millimeter deck, you probably know you should start drawing things with open web steel joists or purlins at 2 meters on center or less. 2 meters on center is a really good place to draw it. If that doesn't equal out, like if you've got something that is a 9 meter bay, well, 2 meters on center doesn't equal out, you might divide that out equally instead. But 2 meters on center or less is going to be a really good place to start drawing open web steel joists and purlins based on the sizing guideline for metal deck. All right, concrete on corrugated metal deck. So we had our metal deck. Now we're taking that same metal deck and we're pouring concrete on top of it. So imagine I've filled this in with Play-Doh and raised it up a little bit. All right, it's the exact same metal deck that we were using in the last example, and the concrete depth can vary. So this is our 38 millimeters right here, and this depth can vary. We always talk about the depth of the concrete from the top of the metal deck to the top of the concrete. I am acknowledging that there is concrete in the flutes. I am not saying there is not concrete in there, but that's not the depth we're talking about. The standard assembly in construction is a 38 millimeter metal deck with 64 millimeters of concrete on top of it. And we're talking about normal density concrete. So if you go to that list of, well, you'll see as we go forward in the term when we talk about loading next week, that when you look at the loading for concrete, there's normal density. And if you look at concrete on metal deck, there is normal density concrete on metal deck. I am always going to be talking about that unless I explicitly tell you otherwise. Always assume normal density concrete on your metal deck. Okay, our sizing guideline now is D equals L divided by 20. All right, we've got open web steel joists or purlins at 2 meters on center. What depth of deck should we use? Okay, let's take a look. We've got 2,000 divided by 20, 100 millimeters. Well, our 38 metal deck with 64 concrete is 102 millimeters. We should use 38 millimeter deck with 64 millimeters of concrete, so that's a total of 102 millimeters. This is the most typical composite metal deck system. Again, that means whatever supports that system should occur every 2 meters. That's the optimal design choice, putting the supports for concrete on metal deck. And if I'm saying concrete on metal deck and I don't give you any other information, I'm talking about 64 concrete on 38 metal deck. The supports for that should be around 2 meters on center, 2 meters or less. And you're thinking to yourself, or I'm sure some of you are thinking to yourself, the metal deck all by itself, and then the concrete on metal deck have the same distance they can span. Why is that? We know, or some of you have probably guessed, that the concrete on metal deck is stronger. So why would we have the same spanning distance? Why would we change the sizing guideline to make the spanning distance the same? Well, here's the thing. These are meant to be used in the range of normal. Metal deck by itself is usually used in lightly loaded applications. So a roof, maybe in an interior residential setting with plywood on top of it, but normally it's a roof. That means it's got relatively light loads on it. Concrete on metal deck, we will often use in 4.8 kPa loading assemblies, meaning these sizing guidelines know that we're talking about using these things in different loading situations. We don't know exactly what these loading situations are, but this is where it's important for you to understand what's normal. If you were going to use concrete on metal deck in an industrial storage situation, you intuitively know that maybe these sizing guidelines aren't right, or the spacing of the supports need to change, because these sizing guidelines assume that things are in the realm of normal. All right, so 64 concrete on 38 metal deck. So the C is concrete and D is metal deck. That's kind of a great shorthand to talk about this. And if you add those up, we've got a depth of 102 millimeters. Our open web steel joists. This is where also understanding what things are normal is important. So our sizing guideline is D equals L divided by 16. So this is how long our member is. And my hands can't show the distances that we're probably talking about for these elements. And D is the depth, how deep it is. So we've got length and we've got depth here. I wish, I wonder if it'll let me draw it easily here. That's length. Did my mouse go away? And that's depth. Sorry, that jumped around a little bit. But you can see we've got length and depth. Now this is important. These are made by a manufacturer, okay? So they have set sizes that they come into in the world. If our sizing guideline told us that this could be 321 millimeters deep, that doesn't help us very much if they don't come in 321 millimeters deep. Drawing that is not going to help us in any way. Knowing what they come in is important. And this is where I'm going to tell you that if you're talking about metric, we would often say they come in 50 millimeter increments. If you're talking about imperial, we would often say 2-inch increments. So look for the cues for what I'm talking about in the question, because yes, these go back and forth and they're not exactly equal. Some manufacturers work to metric dimensions and some manufacturers work to imperial dimensions, just to screw you up completely. So look for my cues. I'll try to be very explicit. If you're talking about a metric project, we'll often write the dimensions in metric, even though they might then substitute the imperial version. So a 300 millimeter might actually end up being 302 or something like that, or 304. But don't worry about that too much. I will try to be very explicit about what I'm looking for from you. So let's see what that means. How deep do the open web steel joists need to be if they're spanning 9 meters? So 9,000, it's just easier to work in millimeters. You could work in meters, that's totally fine. My questions will usually give you the prompt. Are we talking about millimeters or meters here? So 9,000 divided by 16, we get 562.5. Well, that's great. That's how deep we need it to be. But they don't come in that dimension. That's a weird dimension. They're not going to make an open web steel joist at that dimension. We know that it comes in 50 millimeter increments, so 550 and 600. Now this sizing guideline, this sizing guideline said we needed it to be 562.5 millimeters deep. We know it could come in 550 or it could come in 600. Which one do you think you should put on the drawings? The 600, right? If you go smaller, knowing that these are not the final design, that's fine. But if you drew 550, and you did find out that the 562.5 is exactly what we require, you have drawn it too short. Now, what do you think's better, drawing it too shallow or drawing it too deep? Well, finding out later you could have a shallower ceiling is fantastic. Finding out you need a deeper ceiling might wreak havoc on your project. So always think about what you're trying to do here. To find out that you've saved some space later on is usually just an upside. Maybe you can make use of that. Maybe you found out that mechanical had some issues and so you need to deepen those anyway. But always round up. Always go to the bigger size because that's always going to be what's going to save your butt in the end. So we would pick a 600 deep open web steel joist. All right. Assuming it's picking up 38 millimeter deck on a roof or 64 concrete with 38 metal deck on a floor, how often do you think we need them? Now, remember, there's nothing in this that tells us that except the depth of these members. Well, we know if this is being used as our flooring system, the thing that supports it usually needs to be every 2 meters. This sizing guideline kind of has that embedded in it. If you have something at a bigger spacing, this sizing guideline might not work. And these are telling us we need these to be around 2 meters on center. So if I was drawing a preliminary drawing set and I knew I had 9 meter bays and we wanted to use metal deck or concrete on metal deck, I would say I'm using 38 metal deck or 64 concrete on 38 metal deck with 600 millimeter deep open web steel joists at 2 meters on center. So that's like 90% of your project already drawn right there with just 3 sizing guidelines. That's the majority of the structure in your building. Yes, there's more to it, but this is the thing, like you're probably gonna have 100 of these things and you've got your metal deck everywhere on the floor. Yes, there's beams on your major grid lines and columns that support them, but this is the biggest cost of your building and you've already got something you can put on drawings now. Okay, let's go a little bit further. Let's look at our beams and our columns. Now, do you guys remember when we talked about tributaries? And I said that if you came across flowing water in the woods, you would probably always call it a river. But when you look at it in context, you know how much water is flowing in it would make a difference on what you'd call it. But a river is a river is a river. You can use the term interchangeably. It's only when you need to give it some hierarchy that you might call it something else. And I said that steel bending members had that same thing. They're all beams. Sometimes we even call an open web steel joist a beam if you want to get crazy. But they're all beams, but sometimes we give them special names to help us talk about what job they're doing. So remember in that last example, I said there was the things that were 2 meters on center. If it wasn't an open web steel joist and it was a beam, we would call that beam a purlin. So if you see a beam that's repeated, picking up concrete on metal deck or metal deck, and it's 2 meters on center or around 2 meters on center, it's a beam, but it's a purlin type beam. If it's doing something more than that, it's no longer a purlin. Okay, so you should know this list of things. These are the typical steel sizes that exist for different things. We have W sections, we have channels, we have our square and rectangular HSSs, and we have round HSSs. Now there are elliptical HSSs, but we don't really use those that often. So these are the things that are made. This number here tells you approximately how deep it is. It's not exactly how deep it is. It's not right. It's not the right answer in any way, but it's pretty darn close. So a W100 is approximately 100 millimeters deep, and that's going to be good enough for our sizing guidelines. A channel, a C200 is approximately 200 millimeters deep. It's not exactly 200 millimeters deep, but this is what we're going to use for our sizing guidelines. Because remember, if our sizing guidelines aren't exact, this is a pretty good inexact right answer. Okay, steel sizing guidelines. Look at my heading here, steel beams. All three of these things are steel beams. But when I talk about them in context, we may use the term purlin, beam, or girder. So remember, the purlin is the thing that happens every 2 meters on center, or approximately pretty darn close to 2 meters on center. It's usually picking up concrete on metal deck or metal deck. Beams are the things that tend to be on the major grid lines. They are the things that are usually at the perimeter of our bays. If you want to think of it this way, they are usually the beam that is supporting our open web steel joists or purlins. They might also have metal deck on them, so don't let that distract you. But if you see a bunch of things at 2 meters on center framing into the side of it, well, it's probably a beam. If you see open web steel joists and purlins coming into the side of it, it's probably a beam. So what's a girder then? A girder is a thing that is doing more than a beam. What more? I don't know. Maybe you know that it's actually supporting that gold bullion, for example. And maybe you know that a beam is going to be it's going to underestimate the depth we need just a little bit. Now, I have seen people recognize on a set of drawings that the element is a girder. It's doing a lot of work, it's working hard, and they know that they should use the girder sizing guideline. And it tells them it needs to be this deep. And they're like, that's too deep. I'm going to call it a beam instead and make it more shallow. But that's not how it works. It's not a beam. It's a girder. It's doing that heavy job. If you drew it as a beam, you can draw it like that on your preliminary drawings, but when the final design comes back, you will probably find you shortchanged yourself on the headroom you need for that particular beam, which could be a big issue. Maybe your door doesn't fit anymore. Maybe it's right in the middle of a room. Line of sight for things. Over pools and gyms, you need a particular clearance because you're playing volleyball or something like that. So it could have real implications if you underestimate the depth of this thing. So remember though, the beams come in standard sizes, and so those are listed in the CISC Steel Handbook. So that's this bad boy right here. Now, this thing gets reprinted every few years. Every now and then, they will change one member on me. I had for years been using the PDF that was printed out in the 2010 version of it. And then recently I was making question sets. And knowing the PDF was posted and the beam sizes don't change, I was looking at my values in this. And everybody got the answer wrong. And I was super confused because I go in and look. I check the quiz statistics to make sure I haven't screwed up. I'm not going to penalize you guys if I make a mistake. That just doesn't seem fair. So I looked it up, and for whatever reason, in this version, one member had one thing that got changed on it. So Quercus, being the exact uptight thing it needs to be, would only accept that one right answer. Back in the day, on paper, it would have been easy. It would have been pretty darn close to right, and we would have been able to mark it that way. But Quercus kind of means that there needs to be a bit more rigor in these things. So I've gone back and I've checked that all of the answers match all of the things you have uploaded to you. But for right now, you guys can look at this list, all right? We're going to look at this for the most part. All right. So for beams, W's and channels would be the most common. For columns, HSS's would be more common. Beam width. Now, I hate giving the width sizing guideline. Do you think you'd make me a coffee too? He can't hear me. Unless I get line of sight. I usually can't get his attention. So beam width is an absolutely horrid sizing guideline. I'm not going to test you on it for steel. Concrete, I might have some questions on it. But for steel, I don't want to ask you about the width. The reason I'm giving you this sizing guideline for steel is that it's helpful to draw something that looks realistic. It's a very inaccurate thing and only gives a very, very rough estimate that it helps you visualize something. If you follow these in a drawing, it's not going to make somebody go, what are you drawing there? And that's really the goal of this particular width guideline. Okay, so let's take a look at some stuff here. All right, how deep would a purlin need to be, a beam need to be, and a girder need to be if they span 8.5 meters? So maybe we have a project that has an 8.5 by 8.5 meter grid. Simple grid layout. The majority of the elements are going to be purlins at 2 meters apart, supporting concrete on metal deck or metal deck, and they'd be 8.5 meters long. In the other direction, those would frame into beams that are 8.5 meters long. And in some locations, maybe something else is going on that we don't know about, and that is also at 8.5 meters long. So what would the difference in depth be depending on the job this thing is doing? So we know the sizing guideline for purlins is 25, the sizing guidelines for beams is 20, and the sizing guidelines for girders is 15. So 25, 20, and 15. So 8,500 divided by 25 is 340. Let's see if I broke this out. What the? No one has ever noticed that mistake before. So I will fix that. That obviously is supposed to say 340. So that is slide 14. Doesn't change anything. So if it's 340, what beam should we put in our preliminary drawing set? Or what depth of beam should we put? Now this is a purlin. So let's go up and look here. In this list, well, 340 is in between a 310 and a 360. We don't want to go shallower because we might end up bonking our head on it when we do a final design and we find out that it actually is a 360. So a W360 would be good. And we said that channels make good purlins. So a C380 would make a good choice. Okay. Let's see if I did all of them with the right size. All right, so 8,500 divided by 20 is 425. It looks like I typoed that there, knowing that I was going to pick a W360. So 8,500 divided by 20 is 425. If we go back and look at that list, we have a 410, a W410, or a W460. Remember, these are the sizes that exist in the world. We can't write a W425 because that doesn't exist. They don't make it. They make a lot of different steel beams. And let me just see here. In fact, I believe you already have it. There's actual steel member sizes that I've uploaded for you guys. Or maybe that's not until next term. But just to give you a sense, all of these pages in this book are member sizes, and it gets even more than that. So let's look at our W410 set here. Let's see if we can see it zoomed in. So every line on that is a different member size, and W410 went from here to here. So there's like 20 different W410 member sizes. But that's beyond what we're doing in our preliminary sizing guideline. A W410 would probably be something we'd bonk our head on, or we would underestimate the depth of our floor system. So we should go with the W460. So preliminary drawing set, a W460 would be a really good thing to draw on this. And for a girder, this was a member we knew was working really hard. We've got 8,500 divided by 15. We get 567 millimeters deep. We know they don't make a member that is 567 millimeters deep. So if we go back to that list, a W610 is a really good choice to draw on our drawing set. If the purlins are supporting 38 metal deck or 64 concrete on metal deck, how often should they occur? Well, we know they should be around 2 meters on center. So on our preliminary drawing set, I would probably say a C380 or a W360 at 2 meters on center. So if this really was a project with an 8.5 by 8.5 meter grid, we would know that our beams are now all something we could draw on this. So we've got purlins we could draw and beams we could draw, and we've got our concrete on metal deck because those we know would be supported by something at 2 meters on center. So we've got a big chunk of our project sized already, our unknown imaginary project. Okay, a steel truss. It looks a lot like an open web steel joist. It is not an open web steel joist. But an open web steel joist is a truss. It is a type of truss. It is just a manufactured, standardized truss that does light work. It doesn't do heavy-duty work. A truss is something above and beyond. We would often use a truss instead of a girder. So if we see a job that's pretty heavy-duty, we might say that should be designed as a girder, or maybe we'd make a custom truss. So, made by manufacturers and can be custom, but it still often comes in 50 millimeter increments. Not because that's what it needs to come in, but that's just because what we tend to draw on drawings. So if we found out that this needed to be 625 millimeters deep, we could actually tell them explicitly to make this at 725 millimeters deep. So this is something that we could be explicit and make it exactly the depth we need. And I have done that, but unless there's a good reason to, we would draw it at 50 millimeter increment depths. So instead of 725, I would probably say a 750 deep truss. So our sizing guideline is L divided by 12. Okay, what size does a truss need to be if it spans 8.5 meters? So we get 666 millimeters deep. What? There's all kinds of typos in this. What the heck? So that was slide 14. Slide 16. Let's see, did I do that math right though? 8,500 divided by 12, 708. What the heck am I doing here? I'm talking nonsense. So ignore this slide and listen to me instead. Here, I'll see how if it lets me do this neatly. Okay. And this would work out to 708 millimeters. So I would probably say I would recommend that truss depth to be 750. It would be custom made, so we could pick the size. We could explicitly say 708. We could, and this is different than most of the other ones, we know that maybe they could over design this thing and make it 700 millimeters deep. But I'm going to tell you, as a good practice, a good judgment is to always go up a size or go round it up a bit. So we would put a custom 750 truss. So I know what's happened here. I used to, in the slides, have 9 meters for the other question, and this was 8 meters. And then it didn't allow me to compare things, so I've tried to standardize it, and it looks like I didn't update all the math within it. So I apologize for that. So we had, in the last question, a girder that spanned 8.5 meters, and we needed it to be a W610. And now we have a truss, and I said a truss and a girder are often interchangeable. So why would we go with something deeper? Why would we do that to ourselves? So the truss is custom, so there's cost added there. But a truss uses a lot less material. So there's cost saved there. So what other thing might come into play? Well, if we had this girder several times throughout the project, I would definitely suggest a truss. Because what makes trusses and things that are custom made or manufacturer made cheaper is repetition, because they're only designing it once but making it multiple times. So that makes it cheaper. So which one's right, a girder or a truss? I can't tell you. There isn't a right answer. It all depends on context. I'm not going to make you guess that in the questions I ask. I will tell you if it's a truss or a girder. I will be very explicit. But next year, when you do your studio projects, that's up to you. And there's not a right answer. You're going to have to look at the context of your project, whether you would prefer a girder or a truss. Remember, a girder means a solid steel beam, and a truss means a deeper fabricated element that has openings throughout it. So really that one becomes a judgment call. What I've done is give you 2 methods to solve the problem, and you can pick which one's better. It's gonna make me leave this. Damn it. Sorry, folks. I hit escape too many times. I was just trying to get out of that. Let me bring that back up. Oh, no, that's not going to help you. All right. Here we go. Sorry about that. Okay, columns. Columns, the only interesting thing about columns is we wouldn't use angles or channels. We might use an I section. Often, unless I tell you, probably use an HSS. Sometimes you might want to show both as an option. HSSs are just a pretty good kind of normal way to draw your columns. So you can see that I don't have D and L here. I have W and H. Well, that just means width and H is height. So height and width instead of length and depth, because a column is standing up like this. So that's really all it is. So for short columns, I have H divided by 40 to H divided by 20. We are going to be using the H divided by 20. Just don't worry about it. Use H divided by 20 for everything we talk about. Standard sizes listed in the CISC Steel Handbook. So you've seen that list that I gave you earlier up in the slide. That's going to be what you want to use. Stocky W sections, that just means really chunky. The proportions are almost the same. So instead of that 1/2 to 1/3 dimension ratio, columns like to be pretty close to square as we can get. But HSS would be the most common of what we would use. Okay, what size do the columns need to be if they're 3 meters tall? So 3 meters tall, if we were in a building and this is the height of our column, that means this is a floor and this is a floor. That's the height of our column. So sometimes you can determine what the height of a column is if you see something written as floor to floor height, or the difference between the datums in the elevation of a building. Those are all good key indicators to figure out how tall a column is. So what size would the columns need to be if they're 3 meters tall? So we've got 3,000 divided by 20 gives us 150. So that seems like a W150 or an HSS 152 by 152 square, or an HSS 152 diameter would be a really good thing to draw in a preliminary set of drawings. I'd probably go with the 152 by 152 unless there was some reason to do otherwise. All right, let's look at a couple quick examples here for this. So assuming the datum is 3.2 or 3,200 millimeters, size the concrete on metal deck, the joists. So which ones are the joists? Look at these. These are the funny dashed lines, and this says 2J01. J probably means joist. The purlins, there's nothing that has a P in here, but look at these joists switch to this. And they're doing the exact same job as the open web steel joist, and they're called 2B01. So B probably means beam. When we know a beam that can be interchanged with joist is probably a purlin. So it looks like these members are our purlins here. The beams, so we've got a 2B02 and 2B03, okay. 2B01 was our purlins. Hold on a sec, team. Okay, so I ended up changing my mind there. Things got a little distracted. I had emails and phone calls come in about another project, and so I had to take a little break. And then when I was looking at it, I realized I would do this one kind of by hand for you guys. There's enough in a row. Okay, so we're looking at this plan, and we want to size a bunch of the things. They've given us the list of things that we want to size. So I'm going to do it this way so that we're not like jumping forward 5 slides, and I can just make my camera size bigger and smaller. So the very first one, let's take a look at the deck. What does 2D01 need to be? Now, look at this. It shows that 2D01 goes from here all the way to here. Does that mean the deck is 24 meters long? No, it doesn't. If this was our metal deck, remember I said it has multiple supports along its length, even though it comes in one big long sheet. If you looked at those examples we looked at in the past 2 weeks, we could see that it was one big long continuous piece, but it was supported in smaller, shorter segments. So all of this is deck, but its span length is from here to here, or for example, from here to here, or from here to here. All of these lines are supporting the metal deck because this is the direction the flutes are going. So this is 24 meters, and we've got how many gaps or how many spans? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So how far does the deck span? Well, each one of these gaps is 24 divided by 13, and that's the span length. So let's take a look at our metal deck calculation here. Deck 2D01. All right, so the span, or the length that the deck spans, is our 24 meters divided by 13 spaces. Or 24 divided by 13 equals 1.846 meters. We know the sizing guideline for metal deck is, let me just take a look. What did it tell us? Oh, it's concrete on metal deck. So they've told us it's concrete on metal deck, and we know the sizing guideline for concrete on metal deck is that the depth is L divided by 20. So the depth we need is D divided equals 1,846 divided by 20. So 1846 divided by 20 gives us 92.3 millimeters. We know that 64 concrete on 38 metal deck is a really good choice. So 64 concrete on 38 metal deck, which is 102 millimeters deep, is a really good choice. We know that it could go up to about 2 meters on center, so it looks like this is a pretty good choice. We're just a little bit under 2 meters on center. So the next thing they asked us to size were the joists. And those were 2J01. Let's take a look at what our drawing looks like here. All right, so 2J01 spans from here to here. That's its length. Its depth is into the page. We can't see it. This is a plan. So we want to know how deep it is if it spans from here to here. Well, it looks like that distance is 8 meters. So let's make this bigger. We have a length of 8 meters, which is 8,000 millimeters. The sizing guideline for joists is L divided by 16. So for us, it's 8,000 divided by 16. 1,000 divided by 16 is 500 millimeters. So it looks like 500 open web steel joist is a really good choice. We actually know that these are at 1,846 millimeters too. We could just add that extra little bit of information if we wanted. What you might see sometimes is at less than 2,000 millimeters center to center. Just saying that as long as you don't go over 2 meters, it's fine. Or they might say at equal spacing, and then you'd have to look at the whole distance and divide it out. So there's a few ways to write it, but the 500 millimeter open web steel joist is the big question I was asking there. Okay, the next thing is the purlins. So the purlins look like they were the thing that's doing the exact same job as the open web steel joists are right here. So these members were all open web steel joists, and we can tell by this funny dashed line. And then these ones are all our 2B01. We know a purlin is just a beam. It's just a beam that in context isn't working that hard. It doesn't have the big, heavy job. So purlin 2B01. Okay, it's spanning the exact same length. And the sizing guideline for purlins is L divided by 25, or 8,000 divided by 25. 8,000 divided by 25 is 320 millimeters. I would, going back to that list of steel members, use a C380 or a W360 as my purlin. You could say at 1,846 millimeters center to center if you wanted. Now, why would somebody use purlins versus open web steel joist? Well, I can't answer that. Every project is different. Maybe, often if you have a lot of them, the open web steel joists can be cheaper. For example, right now though, I know open web steel joists have a 2-year lag time. That'll probably catch up soon, but that was due to kind of COVID accelerated construction issues. But a lot of them, these are usually cheaper. Maybe you have a headroom issue, and that's why these ones are better. That's a good difference. It's almost 5 inches difference in height. It's going to start to have an impact on things. So there's not a right answer between these two things. Some of it is experience and some of it is about the project itself. Okay, let's take a look. The next thing we need to design. So the next thing is 2BO2. It looks like there's two of them. Now, 2BO2, do we think it's a purlin, a beam, or a girder? And how would we know? Well, we know purlins are the things that do the easy, regular job, usually supporting metal deck, and are at some relatively close spacing, and there's usually a bunch of them. So that meant this. You can usually replace them with open web steel joists. Look at this. We had the two things doing the exact same job. I told you that beams tend to be the beams that support open web steel joists and purlins. So look at this. These span to this side and this side. So this side and this side support these purlins and open web steel joists. But there's no columns underneath them, so the beam spans from here to here. That means that these beams must be the support for these open web steel joists and purlins. So that to me tells me they're doing the job of a beam. You know, it's more than a purlin, but it's not something crazy and heavy duty. So 2BO2 looks like it's a beam, or I would qualify it as a beam. Whoops. All right. Beam 2BO2. Its length was 12 meters, which is 1,200 millimeters. The sizing guideline for beams is L divided by 20, or our 1,200 divided by 20 equals 600 millimeters. Knowing that that's a great place to start, but we want to suggest we want to draw something on our drawings, we would say a W610 would be a really good thing to put on these preliminary drawing sets. All right, let's look at our next one. Is beam 2BO3. Goes all the way from here all the way to here. What? That's not a column underneath? No. See this CA? Remember I told you that means column above. So this beam is really long. It's 12 meters long. And on top of that, it's supporting a column here. There's no column underneath it here. It's picking that up as a load on it. So that means it's doing an extra job. It's not just supporting joists and purlins. It's also supporting a column. So to me, that says it's a girder. Here we go. All right. So girder 2BO3. It's still a beam. It's bending. It's a bending element. So we're still calling it a beam, but we know it's a girder because of the job it's doing. L equals 24 meters, 2,400 millimeters. Sizing guideline for a girder was L divided by 15, or 2,400 divided by 15. Is 1,600. Huh. That list I gave you, there was nothing that deep in it. So we need something custom. A pre-rolled steel element isn't going to work. That's not on the list of the things that we can get. So it seems like beam isn't the right choice, or a girder isn't the right choice. What else did I say we could use instead of a girder? What was similar to a girder? Yeah, that's right. Truss. So let's maybe instead call this 2T01. So we're going to replace 2BO3 with 2T01. All right, so L equals 2400. The sizing guideline is L divided by 12. 2400 divided by 12 equals 2000. So we need a custom truss that's 2 meters deep. So you can see that this is a pretty deep element. If we had floor-to-floor heights that were, in fact, we have floor-to-floor heights. Look at this. Look what they've told us. There are floor-to-floor heights of 3.2 meters. The datum is 3.2 meters. So that means if this is 2 meters deep right here, we only are left with 1.2 meters underneath that truss. So that becomes an important thing in knowing the layout and planning of this. Does that have an impact on it? Knowing very early that you've lost that 400 millimeters from what you might have estimated by designing it as a beam is really important. That could have an impact in a very preliminary stage. And remember, this would be before you've hired an engineer. So these are big structural implications that you're making before you even hired an engineer. So the last thing is, let's size the columns. Okay, columns for the following, we've been told that they're 3.2 meters tall. Okay. So we had two columns. We had column C01, and its height is 3.2 meters. The sizing guideline for column is W equals height divided by 20, or 3,200 divided by 20 equals 160 millimeters. I would go with an HSS 203 by 203. Remember that chart I gave you said they were square and I gave you the major dimension? So this would be a really good thing to pick as your column. Let's take a look at column CO2. Column CO2, if we look at this plan, column CO1 is picking up this tributary area. Column CO2 is picking up this tributary area. We know that it's picking up twice the area, which means twice the load. Let's see what our sizing guidelines tell us. Height equals 3.2, so W equals 3,200 divided by 20 equals 160 millimeters, or HSS 203 by 203. This one has double the load of this one. It's the exact same column. This is 100% the failing in sizing guidelines. This is the problem I've been talking about. It doesn't look at the actual project we're designing and does it based on kind of best rule of practice from like knowing generally what's happening. Now, we look at this and we can guess that this is the second floor. They haven't told us explicitly, but when I see it 2 at the beginning, we're probably talking about the second floor. We don't know how many stories are in this building. What if this was a 50-story building? Does it make sense that that column that might have been sized as a 203 by 203 on the top story would also be a 203 by 203 on the bottom story? No. So you know in your gut that there is something wrong with these sizing guidelines, specifically the columns. The columns are totally out to lunch, but they're a good place to start as long as you understand when you're using them. And it tends to be in mid-range stuff, so a couple stories, not too much. If this was the bottom story of 50 stories, what could you do? You don't know exactly, but if I was drawing this and didn't know how to design something, I'd probably double it or triple it just to make sure I had enough space to not find out that later I needed a column this big, not leaving me any floor space. So having an understanding of its usage can be very important. Okay, here's that all worked out with some notes for you guys. All right, let's move on to wood now. So we've gotten through the steel sizing guidelines. This will start to be quicker because we understand what the sizing guidelines are. Now, wood. We talked last week about nominal versus engineered or mass timber. This slide looks at nominal lumber. All right, what are the dimensions of a 2x6? If you think it is 2 inches by 6 inches, you'd be wrong, unfortunately. It's kind of crazy, I know, but a 2x6 is actually only 1.5 inches by 5.5 inches. So here are all of our typical sizes right here. Here's what they're called, and here's what their actual dimensions are. In metric, we tend not to bother with this. We tend to just convert the actual numbers to metric. So a 2x6 would be the 38 millimeters by 140 millimeters. We wouldn't write it as 51 millimeters by 152 millimeters. We actually use the kind of nominal size. Now, we tend to use these things for joists and studs, built-up beams. Built-up beams mean we laminate plies together. We take a few of them and screw them together. Posts, which would be a 4x4, or built-up posts where we take a few plies of wood and screw them together. You can get full-sized, but it's really hard to do. Full-sized is usually has the sharp edges and hasn't been planed down. It's usually very rough. I've used it for things because it can be a bit cheaper if you go right to the mill and buy it. So I've done it for building docks and things like that. But when you buy it at a lumber yard, so like Home Depot, or maybe you go to an actual distributor, like where they buy it from, if you go there, it's usually smooth and has had the surfaces rounded a bit. That's because they take that full-size element and put it through a plane, and they take a little bit off of all the sides. And that's where that 1/2 inch goes. They take off 1/4 inch off of this side and 1/4 inch off of this side. And you can see for 2x4 and 2x6, it's a 1/2 inch taken off. And you can see in an 8 inch, a 10 inch, and a 12 inch, they take 3/4 off the depth. So really pay attention to that. You're gonna have to convert between metric and imperial for those things. Don't worry, you're gonna see that I do a few of them, and you're gonna see most of them worked out. Plywood is like our deck. Remember our metal deck? Plywood does the similar job. It's the surface that fills in all of the bits. It comes in 4x8 sheets, but it doesn't span 4 feet or 8 feet. It needs something in between to support it. It would be like saying this piece of paper is 8.5 by 11, but that doesn't mean it gets supported only at those corners. It can't even support itself. So we would need something in between to hold it up. So it has typical thicknesses. We're probably going to use 1/2 inch or 3/4 inch. I'll try to be pretty specific about what we're talking about. Eye joists. So wood joists are not to be confused with open web steel joists. They are similar to purlins. I know you're cursing me right now. Why would we have these different names that are similar but mean different things? So in steel, we have open web steel joists and purlins. In wood, we have joists, which are like purlins. They're solid pieces of wood at some regular spacing. But we can have engineered eye joists. So they're a manufactured product, and we would use them instead of joists. So eye joists instead of regular joists. You can see they look like a capital I, and that's why they're called eye joists. These are made by a supplier, but they come in standardized sizes, which I don't have written there. That's weird. I will add that into my slide. Slide 25. I-joist depth. Okay. So we can use structural wood in residential construction. So these are something that we would use when our regular lumber just doesn't work, or maybe it doesn't come in a long enough length. Getting pieces of wood longer than like 20 feet is pretty hard. These elements can come in really long segments. So there's parallel strand lumber, which really just looks like you've taken all kinds of apple peels and roughly laid them out and then glued them together. Laminated veneer lumber is where you actually have full veneers of lumber glued together. The dimensions and availability of these always changes. These are very similar. They're almost the exact same. One is stronger and one is stiffer. Pain in the butt. I have found that if I specify LVL, it just coincidentally, the contractor will call up and say, nobody uses LVL, we only use PSL, this is ridiculous. But they're not exactly the same, so I still have to check it. Does the strength and stiffness still work with this change? So the next project I might use PSL, and coincidentally the next contractor will be like, this is ridiculous, nobody uses PSL, everybody uses LVL. So it has to do with what they're comfortable with working, what they're comfortable working with, what their precedent projects are, where their construction is, where they've worked in the past. So sometimes I'll put engineered lumber on the project and design it for the worst case of either of these. Sizing guidelines, these are the depths they're available in and the widths they're available in. So I think now you can get LVL in 38 wide. Mass timber, this would not often be used in residential construction. A normal home wouldn't use a glue-lam member. There's a long lead time, remember, and they're expensive. You need special people that make them. The LVL and PSL you can actually buy at Home Depot. You just buy it and cut it to length like you would a normal piece of lumber. Glue-lam is something very custom that you would order months in advance, probably. You can curve it, you can make posts or beams out of it. It's not a replacement for regular lumber. These are 2x elements glued on top of each other. So that's 38 millimeters, 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 and that's 38 millimeters. So really, it's conventional lumber glued together in a special way. Cross-laminated timber, we're not actually going to do a lot of it, but it would replace joists and plywood or studs and plywood as your deck or your wall system. So our floor system would be plywood spanning to joists and joists spanning to beams. The CLT would replace that and span to beams. It would be the same thing in a wall. It would replace the studs and the plywood. So it can come in long sheets, but it can't span that far. It needs supports within it. So 60 feet is not how long it can span. That would be crazy. It does need supports in between it. All right, the woods, here's why. I don't like the order of this. Okay, sizing guidelines. Plywood. We're going to use 1/2 inch for walls, 1/2 inch for roof, and 3/4 for floors. It typically spans 16 inches on center, joist spacing or stud spacing. It can do 12 or 20. Sometimes you'll even see 24, but that's the rarity. If it's 24, you usually have strapping. So I'm going to tell you, your wood joists and your wood studs are going to be at 16 inches on center. Just forget about anything else. They're 16 inches on center. Every 16 inches, you've got a joist. Every 16 inches, you've got a stud. So we're not even going to do any sizing guidelines. That's what it's going to be. You might find out, or if you knew that there was going to be ridiculously heavy loading, maybe you'd change something and tighten up that spacing. But the standard would be 16 inches on center. Tongue and groove wood deck spans from joist to joist. It isn't as common anymore. We tend not to see it that often. But 38 is the most common and the cheapest. So our depth is L divided by 40. Now, interestingly enough, remember our metal deck was L divided by 50, and it's made at 38 millimeters thick. The reason metal deck was made at 38 millimeters deep, which is a weird number, why would you make something at 1.5 inches? It's because it was trying to be a cheap, economical replacement for wood tongue and groove deck, so wood elements that spanned. And they came at 1.5 inches. And what they would go do is go around to people building projects and say, hey, we can span a further distance, but you don't have to change anything on your project. Or it could be cheap. This might be cheaper, but you don't have to change anything on your project. Just that 38 millimeters you had reserved for wood, take it out and slip in our 38 millimeter metal deck. So it was really strategic what they did. Okay, if the purlins are at 16 meters or 1.6 meters center to center, what depth of deck should we use? So the size and good line for tongue and groove deck is 40. So 1600 divided by 40, we get 40 millimeters. Well, that's pretty darn close to our 38 millimeters. So 38 millimeter tongue and groove deck spanning 1.6 meters max. Lumber joists, so that's these elements. Well, they are almost always supporting plywood. How often do they occur? Plywood spans 16 inches. These are supporting plywood. These have to occur at 16 inches on center. So that's just going to be standard. Think of these as 16 inches on center. If something's unusual, if something's different than that, you already know your sizing guidelines might not be normal or be able to work the same way. So it's L divided by 16. We know our standard wood sizes. 38 millimeters is the 1.5 inches for a 2x, or 89 millimeters wide. That's getting a little bit unusual. Depth is 89, 140, 184, 235, or 286. So this would be our 2x4, 2x6, 2x8, 2x10, or 2x12. How deep should our wood joists be if they're spanning 2.75 meters or 2,750 millimeters? Well, the joist sizing guideline is 16. So 2,750 divided by 16 is 172 millimeters or 172 millimeters. So let's take a look at this list again. 172. Do we go with 140 or 184? If we went with 140, we could be unpleasantly surprised later when we find out that it needs to be deeper. If we went with the 184, maybe we've left a little bit of wiggle room in our back pocket. So I would strongly suggest, and when I ask you in an exam or an assignment, I'm looking for the one that's bigger. So we would want the 184. So 184 is 38 by 184, or a 2x8. If this was supporting plywood, how often does it occur? I already asked you this. It's 16 inches on center. So if you were writing this in a metric project or an imperial project, we would write it as a 2x8, knowing that it is not 51 by 203. It is actually 38 by 184 because it's actually 1.5 by 5.5 in dimension. So a 2x8 at 16 inches on center, or a 38 by 184 at 400 millimeters center to center. Engineered eye joists. Now, these are not cheaper than wood. So why would we use them? Well, often, because they come in deeper depths and they're slightly more efficient, they can span longer distances. So if you've maxed out what wood regular joists can do, but you want to just stick to wood construction, you can buy these the same way and keep wood construction. So it keeps the design down, it makes it easier to build, it keeps nice light elements. You've got all one type of system. You often need to order these in advance, so there's a little bit of a lag time with them, but they're pretty quick to churn out. Their local engineer, or the person who's supplying them, will design them. So your base building engineer would just do a quick sizing check. Okay, the sizing guideline is D equals L divided by 18. So it looks like I did put the depth here. So an engineered product, that depth varies with supplier. Typical depths would be 240, 302, 356, and 406. Different suppliers have different depths. And so look, you can see here that these numbers have nothing to do with the depth. These have to do with the top dimension and their vibration criteria. So don't worry about these specific names. What I would be looking for is for you to call up one of these depths for your eye joists. Okay, how deep should our eye joists be if they're spanning 7 meters? Okay, so our sizing guideline is L divided by 18. So 7,000 divided by 18 is 389 millimeters. Let's go back and look. That one would be too small, so it looks like we'd need to go with the 406. So the closest is a 406. I would specify 406 engineered joists. The engineered would replace the eye. You could say eye joists or joists, engineered joists. If these were supporting typical plywood floor, how often would we need these to occur? Well, that's right. We know the plywood spans 16 inches, so 16 inches center to center. So 406 engineered joists at 400 center to center. Wood beams. Okay. The joists were in a separate category. We have lumber beams. So lumber is going to be our 2x material, our regular lumber that we can go buy at Home Depot. Engineered beams, we're talking LVL and PSL. Possibly glulam, but that's not very common. Engineered girders are the same as the engineered beams, so we're talking PSL, LVL, and possibly glulam, but it's when it's doing a bigger job than just a regular old beam. So these two things, the beams, would be doing a regular job of supporting our joists. So remember, our joists are like our purlins, and these beams are like our steel beams. They're all beams, but these are just regular beams. These ones are supporting the purlins or the joists. The width, I hate giving this sizing guideline. D divided by 2 to D divided by 3. I have tried to be very careful to make it so that the answer is very obvious for you, so you don't get caught up in doing this calculation. Here's the important thing to remember. Lumber beams are built-up beams of 2 to 4 plies of standard lumber sizes. So that means that if you see that we're talking about a beam, 1 ply is not enough. It will automatically be 2 plies together. Joists, 1 ply. Beam, minimum 2 ply. So if you see a question that says which one of these is right and you know it's a beam and you see 1 ply written, that is not the answer. The one with multiple plies are. We can do 5 plies of things, but it's a little weird. Beyond that, we don't do that many plies. So 2 to 4 is the standard amount of plies. Oh, and then I missed one. Lumber posts or columns is H divided by 30. Okay, let's do another example here. Let's do one with our wood set. Okay. We've been told the datum. What should the preliminary drawings for the plywood deck? 2J01 as a joist, 2J02 as an eye joist, beams 2B01 to 2B03, and columns C01 to C05B. Pay attention to the column above on 2B03. So look at 2B03. It's got a column above there. So we've got dimensions. Looks like we can figure most things out. we've got labels on things, so we've got some of the key things we need to proceed. And they've even told us the floor height, so that would be how tall our column is, right in the question. So we want to do up a preliminary set of drawings. So we want to put some reasonable sizes down on this. Okay, let's see what this gets us. So the very first one is the plywood deck. What should be on the preliminary drawings for the plywood deck? They haven't told us if this is a floor or a roof. I'm going to tell you, I'm going to guess it's a floor because they put a 2 here instead of an R. So remember I said a floor should be 3/4 inch plywood. So that's the very first one. 2D01 is going to be a 3/4 inch. Look at me. You can't see what I'm writing. It's going to be 3/4 inch plywood. You might see that written as 19 millimeter plywood. It's going to be supported at 16 inches on center. So supports at 16 inches center to center, because we know it's typical. Oh, and actually they even told us directly in the question. Look at this. They said 2J01 is at 16 inches center to center, and 2J02 is at 16 inches center to center. So it looks like that matches exactly what we would have thought was appropriate anyway. So 2B01, looks like we've got 4 of them. They're all 4 meters. Perfect. They look like they're just supporting some joists. That worked. Oh, let's not do 2B01. Let's do 2J01 and 2J02 first. Okay, so 2J01 and 2J02 span 4 meters. So they both span the same distance. This one they've asked to be regular joists, and this one they've asked to be an I joist. We don't know why. Maybe mostly they want to make that comparison. So we've got 4 meters of span. So 2J01 joist. The length is 4 meters. We know the sizing guideline is D equals L divided by 16, or 4,000 divided by 16. 4,000 divided by 16 equals 250. All right, 250. The next appropriate size that looked like it worked was a 38 by 284, which we know is a 2 by 12 joist at 16 inches center to center. Okay. 2J02 was an I joist spanning the same distance. The sizing guideline for an I joist is L divided by 18, or 4,000 divided by 18 equals 222 millimeters. If we went back and look at that list of available I joists, one of them was a 240 I joist at 16 inches center to center. Or maybe I'd say 400 center to center because it's metric. So I gave you the available sizes of I joists, so the typical ones. So what would we do? This one is shallower than this one. These are cheaper, more readily available. You can just go out and buy them. They stop being cheaper if you need a ton of these. If you need a lot of these can be cheaper. There's a bit of a lead time though. So if you only need a few of them, I'd go with this. So if you were building one house, I'd probably go with this. If you were building 50 houses that were all the same, I'd probably go with this because it would be cheaper. If I had a situation where the spans got longer, maybe these are 8 meters, maybe these were only 6 meters. Look at this. This was almost at the limit of what was available of a 2x12. These have deeper sizes and they're more efficient. So if we have an unavailability issue because they simply don't work, I-joists become really handy. Okay, let's take a look at our next question. The next one was 2B01. So 2B01 spans 4 meters. It's supporting our joists and I-joists, so I think it's fair to call it a beam. Actually, look at 2B02. It's spanning 5.3 meters and just picking up some joists. So I'd say both 2B01 and 2B02 are a pretty good choice as a lumber beam, just a normal old beam. So 2B01, beam, or a lumber beam. All right, so we know it needs to be multiple plies. Right away, we know it needs to be multiple plies. Our length is 4 meters. Our sizing guideline is L divided by 14, 4,000 divided by 14. 4,000 divided by 14 is 285 millimeters. 286, I guess. It looks like our 2x12 is going to be a good choice. I know I said never go down in size, but 2 millimeters, I'm not going to freak out about 2 millimeters here. Any ones I give you in your assignment, I try to make them really obvious that you have to go up. I try not to fiddle around with that on you. I try to make it super duper obvious. The width, we know that this is not just one ply that is 1.5 by 11.25. We know we need multiple plies. We know that. How many? I hate making you guys do this part of it. So I've tried to make it as obvious as I could, but know that it's more than one ply. And it could be anywhere from 1/2 to 1/3 of this dimension. Now, is it this dimension? Is it the 12 inches? Is it whatever we calculated? What if this had been calculated as 250 like this? Would we have used the 250 or would we have used the 284? Those are all really good questions. And the answer is, I don't know. This is a really inaccurate method to do things. So mostly what we want to do is draw a few plies. But let's just see what this one shook out at. I'll do the 286. So 286 divided by 2 is 143 divided by 38 shows we'd need 4 plies. 286 divided by 3 divided by 38 shows we'd need 3 plies. So it looks like 3 to 4 plies is going to be the right answer for this. So I would probably go with 3 plies on a preliminary drawing set. But again, this is a really inaccurate method. So 3 or 4 ply of 2x12. So we would have 3 pieces of it that have been screwed together. So each one of these is a separate 2x12. And these have been all screwed together. And there's very specific requirements on that screw pattern. Okay, let's do our 2B02. Our 2B02 beam. Our length was 5330. or 5.33 meters. Our sizing guideline, is length divided by 14, or 5,330 divided by 14 equals 381 millimeters. We don't have any lumber that works for this. Regular lumber doesn't work. So we're building a custom wood home, say, and this one element doesn't work with regular lumber. Do we switch to steel? That seems like a bit of overkill. So what I would suggest is trying some of our engineered lumber. So this would be an engineered beam. So as an engineered beam, which means PSL or LVL is what we would want to go with for this. Okay, so our length hasn't changed, but the sizing guideline is L divided by 16, or 5330 divided by 16. 5330 divided by 16 is 333 millimeters. So if we go back and look, both PSL and LVL were available in a 356 element. So PSL or LVL 356 beam. I'm not going to ask you for anything more complex than that with these. We could look at the width on these. I'm not going to go that far on it. You can see that in the example that I have posted, it's worked out with the depth into it. Okay, 2B03. 2B03, they pointed out that there was something funny with 2B03. 2B03 has a column above. What do we know the second we hear column above? We know girder. That seems like it's doing an extra special job. Also, look at this span. It's double what this span was, and regular lumber didn't work. So we've got a very long span that we know regular lumber already right off the bat won't work for. So we're talking about engineered products, and it's a girder. So let's take a look at what that means. Okay, so girder, an engineered wood product. Our span is 10,670 millimeters. Our sizing guideline for an engineered wood product girder is L divided by 12. We can plug this into our calculator. Oops, no. Divided by 12, we get 889 millimeters. Now, I said glue lam is stacked pieces of lumber, and they tend to be 1.5 inches deep. Not always, though. Sometimes they will make ones that are, especially if it's European, they might make them at 30 millimeters. They might shave them all down so that when they glue them together, they all behave the same, but equal our depth that we have in our drawings. So this one, I'm not going to get too fussy about what depth you have to put on here for this. Ones where I say, give me the exact depth you sized, I'll try to be very explicit about that for everything. The last thing we have is column C1 to C05. It told us our datum, which is our height, is 2438. So datums, if we have a building like this would be our ground. That's a datum, that's a datum, that's a datum, that's a datum, and that's our ground. And then each one of these is a datum. Sometimes they'll refer to it from 0 and name off the datums, or they'll refer to them as a floor-to-floor height. But what we're measuring are these values here, which is our story-to-story height. Yep, there's floor depth in here. I'm not gonna argue about that. But what we tend to use in our preliminary sizing guidelines is our datums. Okay, so they gave us our datum. We want to know what dimension we need here. And our sizing guideline is height divided by 30, or 2438 divided by 30. 2438 divided by 30 is 81 millimeters. Okay, well, we know that an 89 by 89 post would work. So 89 by 89, which is a 4 by 4, which is really a 3.5 by 3.5, works. So that's something that could work. I said a column could be built up smaller elements as well. Well, we know the minimum dimension is 81, which means we have, if we're doing something that's built up, we need to know how thick that needs to be, or how many plies. So 81 divided by 38 is 2.1, so we need at least 3 plies of this. So maybe 3 plies of 2 by 4. So 3 2 by 4s, or 3 things that are 38 by 89, which is 38, I think it's 114. So what we would have for this three plies, where this dimension is 89 and this total dimension is 114, because we need our minimum dimension to be 89 on both sides, or 81 on both sides. So the available first depth is 89. 2 of these would have only been 76 and not wide enough for us. Column C1 to C5, all the same dimension. Let's take a look at that. Seems crazy, because they are all doing very different jobs. Look at this one here, CO4. It's picking up all of this tributary area plus half of whatever that column above is, whereas CO1 is picking up that tributary area. So they are not doing the same thing at all, but yet the sizing guideline tells us they're the exact same. So again, that's where the sizing guidelines are horse poop. Sorry. I've gotten a complaint in the past that I swear too much in my lectures. I've tried very hard to stop doing that, but I grew up next to the trailer park where Trailer Park Boys were filmed, which means that there's a lot of swearing where I'm from. So bear with me. If you hear it slip out, I apologize in advance. I am working very hard to correct that. My kids hear me swear all the time. They know not to. It's never been a problem. Okay, so here's all of that worked out for you with lovely little notes if you need to go back and kind of just read it through. All right, final one we're going to do is concrete. I'll try to make this one faster because we've gone through a few of them now. So concrete we tend to use hollow core we tend to use in combination with steel, but it goes in the sizing guidelines for concrete. Remember, if I didn't say this at the beginning, there is a PDF of sizing guidelines for you posted. Please print. If you're going to print something off, print off those sizing guidelines. You should be sleeping with them under your pillow. That's a thing you should have on hand forever and always. Recently in the second year studio comprehensive, Paul Fast, who's an engineer in Vancouver, was one of the guest studio crits. And he reached out to me. He's using the sizing guidelines I've created now, where he teaches somewhere in the States. So he does the structural component for the architecture lectures somewhere in the United States, and he's now using my sizing guidelines down there. So these are made and engineered by the fabricator. So it's like our I-joists and our open web steel joists. They come in standard depths of 150, 200, 250, 300, 350. Depending on the supplier, they will call these 152, 203, 254, 305, and 356, because those are the imperial kind of designations of it. There are 3 major suppliers in southern Ontario, and they all actually make them at slightly different depths. They don't all do metric or all do imperial. They literally each pick one and do them slightly differently. So you have to be very aware of that in your drawing, that you might get a few millimeters of play out of that. I would always recommend drawing the deeper one, even if you call it I would maybe call it the 350, but I would maybe draw the 356 just to be careful. Okay, so if the beams are at 8,000 millimeters or 8 meters, so the beams are at 8 meters on center. Remember, this replaces our metal deck and our joists. So we've just gotten rid of that. Usually we use hollow core in a steel building. So we've got major beams at 8 meters on center. What depth of precast should we use? Well, the sizing guidelines tell us that 200 millimeter hollow core deck would be a great thing to use. Now, I said hollow core comes in these typical sizes, but that 200, 250, and 300 are the most common. The others tend to only be economical if you're using 200, 250, or 300 in the project and you don't want to do cast in place for little tiny zones. So they make those, the other ones, really only to sell to people that are using their product in the rest of the building. So if these are the common ones, could we know what the typical spans for those common hollow core products are? Yes. 200 hollow core slab, well, we take our sizing guideline and we work it the other way. If we know what depth they come in, we can know how far they can span in typical conditions. So 200 hollow core slab is going to typically be used in 8 meter or less span buildings. 250 hollow core, we could use it up to 10 meters. So anywhere from just over 8 to 10 meters is going to be a great application for 250 hollow core. 300 hollow core is going to be great for anywhere above a 10 meter span to a 12 meter span. And this is pretty good knowledge to have, that you know kind of at a base minimum what you're going to use. All right, one-way slab versus two-way slab. We talked about that last week. One-way slab is when we have our beam lines parallel to each other and our slab spans in between it. So we only have supports at the ends of our paper, so you can see how the paper wants to bend, versus having supports on all 4 sides where it would bow down in the middle like a trampoline. So this behaves similar to precast and hollow core, with load going to only the 2 major sides. It's custom. Remember, we put our plywood on the other side of this, so we're picking the depth, except most fabricators are going to make it in 50 millimeter increments. Even if you tell them to do otherwise, they're going to make it in 50 millimeter increments. I usually only don't do 50 millimeter increments when it's something highly customized. Maybe it's a feature element, something that's going to get a high amount of priority. If you're talking about a condo, don't write anything that's not at 50 millimeter increments, because it's just not going to be, they won't do it. Okay, so D is length divided by 18. Okay, how deep does a one-way slab need to be if we're spanning 4 meters? Okay, we've got our 4,000 divided by 18, gives us 222 millimeters. We need a 250 cast in place concrete slab. Perfect. If 200, 250, and 300 cast in place concrete slabs are the typical depths formed in Ontario, how far can they span as one-way slabs? Again, this is handy knowledge to know. It would be each of their depths times 18. So a 200 one-way slab is about 3.6 meters. It's not very far. A 250 slab is about 4.5 meters, and a 300 slab is about 5.4 meters. These aren't very long spans. This is why often we end up having two-way slabs, because often the grid lays out pretty nicely in a two-way slab. So let's take a look of when we can use a two-way slab. Okay, the load is shared between supports on all sides as long as the ratio, that's a typo, 44 ratio is less than 2 to 1. So that means that the ratio of this side to this side is less than 2 to 1. If one of these sides was really, really, really long, and I showed you this last week, it's behaving like a one-way slab. You can call it a two-way slab, but it's not, and you'll under-design things. So again, typical sizes are 200, 250, and 300, although you can cast other sizes. Again, try to make it in 50 millimeter increments. That's what it's going to be built at. Okay, how deep does our two-way slab need to be if we're spanning 8 meters? Well, 8 meter or 8,000 divided by 30 is 266, a 300 cast in place concrete slab. Okay, in Ontario, I told you what the typical slab depths are. So what are the typical span lengths in concrete in Ontario? Well, a 200 two-way slab is going to be 6 meters. A 250 concrete slab is going to be 700 or 7.5 meters. And a 300 concrete slab is going to be 9 meters. Most concrete condos in Ontario tend to be at a 6 meter grid. We're pushing them to 9 meter grid, but this 6 meter grid is really great for a 200 concrete slab. And so that's pretty common. 6 meter grid works really well for layouts for office buildings and condos. It just works really nicely. Okay, our concrete beams. So again, everything in bending is a beam. Even our slabs are beams, if you wanted to think of it that way. Our metal deck is a beam. They're all beams. We just give them special names. So a concrete beam that's just doing a regular old job of picking up a slab, going around, minding its own business, being a beam, it's going to be length divided by 16. If you see a concrete beam that's doing something more than a regular old job, it's going to be a girder. And so then it's length divided by 12. Ugh. Beam width, again, total horseshit. We're going to draw it as d divided by 2 to d divided by 3, but it can be really wide and shallow. It can be really wide relative to its depth. So don't put too much into it. Don't get caught up on that. Here's the fun thing about a concrete beam. The top part of it can be part of a slab. I'm going to draw it here for you. So, if this is our beam, that can be the top of our slab. And that can be the bottom of our slab. So that would be the slab depth, but look at this. I want to get out of. Oh, that's weird. I didn't know I could do that. No. What the heck? I've done something crazy now. I don't want a pen. I just want to go back to normal stuff. All right, well, this will make do for now. You can see that the tops are aligned. So we've pushed that beam up into the slab. The beam depth is still from here to here. Actually, I'm going to draw that. So that's the beam depth. So we've superimposed them in on each other. Because you can run the rebar through each other, that's a really fun advantage that you can get with those. Okay. All right, so concrete sizing guidelines, we have them written here. What depth below the slab do we need for a beam spanning 9 meters if the slab is 200? So we need to figure out what the total depth of the beam is, and then they've asked us how much depth below the slab is there. Hot tip, sometimes I ask for the full depth, sometimes I ask for the depth below the slab. Pay attention to that in the assignment and in the exam. For those of you that have listened to this lecture and heard me say those words, you're going to have no problem and you're going to get all the marks for that. Okay. So if its length is 9 meters, the sizing guideline is length divided by 16. We get 562.5 millimeters. We like to build these in 50 millimeter increments. We're going to round up to 600. So the beam projects 400 below the slab. We're going to just do sizing guidelines for widths I hate. It's more just to draw something that doesn't look totally out to lunch. So anywhere from half to a third. A third's probably a pretty good one just to make it look not weird. So 600 divided by 3 is 200. So I would draw a 200 by 600 beam, and there's 400 millimeters projecting out below the 200 millimeter slab. Concrete walls and concrete columns. They're custom made on site, typically 50 millimeter increments, but not required. Walls wouldn't tend to be less than 200 millimeters unless it was a short and lightly loaded wall. I can tell you that is not common. It's something custom, and it's usually heavily designed and something very specifically requested by the architect. Okay, what would the size of the columns and walls be for a building with a 4.2 millimeters story to story height? So it's the same story to story height, and we have walls and columns scattered throughout this project. We can very quickly figure out what they'll all be. Okay, the height is 4.2 meters. The sizing guideline is 20 for columns and 25 for walls. So the columns need to be 210 dimension at least. So I would pick a 250 by 250 concrete column. The walls, they say 168. So I would go with a 200 millimeter thick wall. So this is great. We've got our columns and walls for this project. What if the column was on the ground floor of a 45-story building? Do you think our 250 by 250 concrete column cuts it? No. You intuitively know that that wouldn't work. You know that it's got to be bigger than that. Can I tell you how big it should be? No, because for that one, you're going to have to start doing final design. But I would tell you, start with these sizing guidelines and maybe start to bump it up every 5 stories. Just totally made up. I probably told last year something different, but this is simply to help you draw it on your drawings. So if you were doing multiple stories, bump it up 50 millimeters every few stories. So masonry. So this would be our block. So remember, block comes in 190, 240, 290 widths. 190 is the most common. If brick, it's usually 90 millimeters, and there would be multiple wides, and they put mortar in between. So it would still work out to be 190. So we have a difference here between load-bearing and non-load-bearing partitions. Remember I told you earlier on that that there was things we had to do to make it non-load-bearing at the top, and we looked at typical details. So that would be very important. If it supported the roof and actually held load, we would have to use this sizing guideline. So it's height divided by 200 or by 20 for load bearing, and h divided by 36 for non-load bearing. So what would it need to be if it was that same concrete building? Well, our load bearing partitions would be 240 divided by 20, or 210, meaning we'd want to use the 240 block. Whereas in the same building, the non-load bearing partitions could be 190. So designating your load bearing versus non-load bearing walls becomes very important with masonry construction. Okay, this is just some quick information because nobody ever tells you this and you need to know it. So this is a good place to tell you. Masonry sizing guidelines for brick veneer. So that's just the brick that goes on the outside of your building. Starting at grade, you can go up to 11 meters, but you need shelf angles story to story. So at each story, you're going to put an angle that's going to support it. Brick veneer is laterally connected to the building every 600 millimeters. So that means if this is our brick wall, it can go up quite high. If we have multiple stories of it, we would fasten it, we would put a steel angle to support underneath it. So if this is story 1 and this is story 2, we would put something here that supports it and fasten it back to the building. And if we had, we actually tie the brick back to the building every 600 millimeters. So what does that look like? So this is our brick at a story. So let's say this is a story height, and then this is our plywood and stud. This is our support for the brick, and it's an angle that's attached back to the building. And then they tie this back with ties every 600. So that's just standard for brick. A lot of this is typical details. That wouldn't really be something that I would spec. If we start to get weird things, I will design the shelf angles. Okay, sizing guidelines for cantilevers. What happens when it's a cantilever? If you guys remember our deflection criteria, we would have the sizing guideline. So that's what we're gonna do, or have the deflection criteria. We're gonna do the same thing here for sizing guidelines. Using the cantilever length, the rule of thumb would be half of whatever the beam rule of thumb you were using was. So for a steel beam versus a concrete beam, 8 meters is our backspan and 4 meters is our cantilever. It would be a 400 deep steel beam or a 500 deep concrete beam, or a 400 deep cantilever steel and 500 deep cantilever for the concrete. So this could be a uniform element all the way through. Perfect. What happens if we mess with these backspans and relative dimensions to each other? So this cantilever was half of the backspan, and we're halving our sizing guidelines. What happens if that's not what we're doing? What if this is 10 meters and this is 4 meters? Well, we would have a 500 deep steel beam. Obviously, we'd bump up the size. I'm just trying to show you what the calculations show. And our depth for our cantilevers are this dimension. So if this was supposed to be one continuous element, we can see that the 500 is deeper than the 400, which means we're going to want a W 530, I believe, for our beam, our steel beam here. Or we're going to want a 650 deep concrete beam here. What happens if we have a really short backspan? Well, now our cantilever depth might govern what we draw on that drawing. Now, concrete's interesting. Concrete, we can actually make it discrete. We could actually draw them different. So if it was a steel beam, it would be, I'm drawing right over the joint here. Maybe we want it continuous. So this is this joint right here. Would make it one continuous steel beam. What if we needed it to be different depths? But it's a cantilever, so it has to be continuous. we would need to make that zone there act as if it was one continuous beam. Concrete, we just kind of get that for free. I'm off my page. Concrete, we can form it up like that. We can make it look weird and wonky because we know we've got rebar or reinforcing inside that doing the majority of the work. Okay, forever tips. The sizing guidelines are going to help you with all of your preliminary sizing. The rules are not perfect. Use them with a grain of salt and understand your constraints. So stop and think about what you're trying to do with those sizing guidelines when you apply them. The studying and project tips, same as above. I say here, memorize the sizing guidelines. You should just have them with you all the time. I have mine downloaded on my phone and tagged and saved to reference all the time. If you guys remember in the very first lecture, I said sizing guidelines are going to be your secret weapon. Most engineers forget their sizing guidelines, and they try to do all of this work when on a preliminary set of drawings, they could probably just use the sizing guidelines. In early communication and feedback with architects, the sizing guidelines are a phenomenal thing to have memorized. So that's the end of week 5. Next week, we start getting into the real stuff. We're going to talk about loads. What actually gets put on our buildings? What are we trying to support? And we're going to start tracing that all the way through the building to figure out what the internal loads are on our elements. Okay, so next week, we're going to start doing fun stuff.